Hi, I'm Stevie C and the place to be. After repairing this LED RGB PARcan, I thought I'd make a video about designing and assembling one. For decades, both the theatre and live events industries have used PARcans for lighting, PAR meaning parabolic aluminized reflector. While there are still some applications where you'd want to use tungsten lighting, LED lighting is often cheaper, is more energy efficient, has built-in dimming and other features, and is generally good enough for most applications. With new laws banning the sale of traditional PAR lamps, these older lights are being consigned to landfill. I like repurposing older lighting equipment, as you'll know from my projects where I convert old tungsten fairy lights into LED lights. So I decided I would design and manufacture a PARcan retrofit PCB. This lamp is called a PAR 56 because it measures 56/8 of an inch in diameter, or 7 inches. It was just a simple matter of converting inches into millimeters, subtracting a little bit for manufacturing tolerances, drawing a circular outline in sprint layout, and starting to experiment with different component layouts. After various variations of design, I settled on this one, which supports 3 or 5mm LEDs with 1/4 watt current limit resistors. You'll notice the space around the outside. This is because I didn't want any electrical connections near the metal chassis of the PARcan. It has a common positive supply rail and 3 negative rails for independent 3-channel control for R, G and B, or any other LED color combinations you wanted. It's also a single-sided board because I know how much of a pain in the arse dual-layer boards are to work with. I designed my PCB for use with a 12-volt power supply, as these are fairly common and can be sourced from reputable suppliers, such as Rapid Electronics, CPC, RS Components, Mauser, DigiKey, Maplin, etc. It could also be run from a car battery without the need for a power inverter or generator. On my PCB, the LEDs are connected 3 in series with a resistor between the voltage rails. To calculate the value of current limiting resistor, I subtract the LED's forward voltage from the supply voltage and divide that by the desired current. So for the reds, which drop about 2 volts each, there's 3 of them, that's 6 volts, so minus the supply voltage, and I don't want them to run any higher than 20 milliamps. So that's about a 300 ohm resistor. The nearest value I have in stock are 330 ohms. So we'll put that into the calculation. So 6 volts to drop divided by 330 ohms equals about 18 milliamps. So likewise with the green and blue LEDs, which drop about 3 volts each, there's 3 of them, minus the supply voltage, that's 3 volts to drop across the resistor. So again, dividing by the max current we want flowing through the LEDs, about 150 ohms. So again, the nearest value I have in stock is 180 ohms. So I'll plug that into the calculation. 3 volts to drop divided by the 180 ohms gives us about 16 milliamps, 16.5 milliamps, something like that. So again, well within the operating characteristics. So as ever, I'll start by forming the resistors with this component forming tool, and we'll jump into time-lapse to solder everything in. So cue the music. I'm starting to realise this isn't the most ergonomic design. But anyway, that's all the red LEDs soldered in. So before we go any further, I'm going to solder in this battery snap onto the power rail so I can test the red LEDs. I forgot about the design. There's actually 2 voltage rails, one for the middle, one for the outer rings. So we've got one dead LED there. This appears to be a solder bridge. Yeah, I got it. Well, hey. Right, so that's the PCB now assembled. This is now day 2. So let's go ahead and get some power into it. Okay, now as well as making my voice sound a bit weirder than normal, my new camera setup isn't letting me fit as much into frame. So all we've got here is we've got mains power coming in here. That's the voltage tonight. I've got a 3 amp 12 volt adapter on an extension cable just because that obscures the screen from the camera. The 12 volts leaves the DC jack and enters that barrel connector. That leaves there down the positive. That goes into the ammeter. The ammeter comes out into the Wago, feeds both the positive rails of the PCB. The voltage comes back on the RG and B channels. They're just commoned into the negative of the power supply. So we can test the whole board on 12 volts. And that is bright. So I've designed the PCB to be as universal as possible. For example, if you wanted a static wash, like it's doing now, you could just assemble it into the PARcan with a suitable power supply and leave it to look amazing as it is. However, I bought one of these LED DMX controllers, and that's what I'll be using to drive my PARcan. Equally, for simplicity, you could use one of these LED tape drivers that come with a little remote controls. That would give you basic color control and chase functionality. Again, that's 12 volts in and the common positive rail with the LED switched to the neutral. So to test this, I'm going to power it from the 12 volt supply as before, but now I'm going to test the functionality of the DMX controller. So to do that, I'm going to write a basic chase sequence in my DMX software. I'll send it out from the computer in my DMX interface. It will then run via my buffer. Doesn't really fit in there, but there you go. So just check first of all, do we have red? Green, blue. So if you're wondering, I've unplugged the DMX interface, so that does hold the data from the last known state. So I know there's some problems with it, the most obvious one being the DMX dip switches. They're located on the controller PCB, which is stuffed in the back of the PARcan where it's inaccessible. But this is just a proof of concept prototype. And to be honest, quite a lot of my lighting fixtures from professional sources, I've set the addresses once and never needed to change them. Likewise, for an installation, you would set the addresses and forget about them. So So anyway, now that that's assembled, I can go ahead and compare it to the Pulse PARcan. The Pulse Eco Par with the 151 LEDs will be on the left. On the right is the iSource 156 with 240 LEDs. So I'm not sure how well this is coming across on the camera. I've had to throw down a bit of white paper to give the camera something to focus onto. The one I built seems to be quite a bit narrower, but that will of course depend on the type of LEDs you use. So the Pulse is a much sort of wider flood. So even though I've got 96 red LEDs and only 72 green and blue LEDs, there's still a definite shift towards the green and blue end of the colour spectrum. But of course this can be compensated for with different values of dropper resistors. If you added up the cost of a decent power supply from a reputable source, the LEDs, the DMX decoder, and the soldering consumables, not to mention the cost of the PCB itself and the time to assemble it, it's probably not going to be cheaper than buying a brand new LED PARcan outright. But it will give you the option of having a PARcan as unique as you. Instead of red, green, blue, you may wish to have, for example, cold white, red and amber, or ultraviolet, blue and pink, or pink, pink and more pink. And it will save another old PARcan from landfill. If you liked this video, there's a like button somewhere that you can click, tap, smash, or otherwise abuse. If you're watching this in 2021, you can be the first to leave a comment. If you're watching this in 2045, you can head on over to the comment section where someone has started an argument about something that's not remotely relevant. So until next time, thanks for watching.